Let's turn our attention now to power and energy in a resistor. And before we get into equations specific to power for electric circuits, let's just remember what power is. Power is the rate at which energy changes forms. And we can express it using this equation: change in energy divided by the change in time, or by how much time it takes to make that energy change. So if I have some power rating on some device, say I'm using a 1,000-watt microwave to heat up my food, and I run it for 30 seconds to get that thing hot, I can figure out how much energy it took, regardless of the fact that it's an electronic component. That's just a definition for power. So power is energy over time. In that case, if it were a 1,000-watt microwave, my 1,000 watts or 1,000 joules per second goes in for power, and my 30 seconds goes in for time, and I could multiply both sides by 30 seconds and get 30,000 joules of energy used in the microwave there. So we'll keep that in mind as we go back and forth between energy and power with resistors. Now, as far as the energy that we're talking about, when we run a current through a resistor, the resistor gets warmer. And so this might be called heat energy or thermal energy. More correctly, though, the term we'll use for this is internal energy. So this is just the vibrations and rotations of the atoms and molecules that make up the resistor. They're all wiggling in there, and it makes them wiggle faster. We experience faster wiggling atoms as warmer, but internal energy is how we describe the kinetic energy of the very, very small pieces that make up larger objects. We can get an idea for what this relationship is going to look like to figure out power when we're talking about an electric circuit by thinking about the units we use for current and for voltage. For current, we use the ampere, which is just shorthand for coulombs per second. And for voltage, we use the volt, which is shorthand for joules per coulomb. If I were to take the units for current times the units for voltage, I'd have coulombs per second multiplied by joules per coulomb, and my coulombs would cancel, and that would leave me just with joules per second. Now, we had another name for joules per second. We called that a watt. So this kind of helps us to see, oh, hey, if we took the current times the voltage, the units would work out right for power. And it turns out it's not just the unit, it's actually the numerical value that works out. So P equals I delta V is an equation that we use to calculate the power through a resistor. Now, for a resistor, so long as it's an ohmic resistor, as they will be when we deal with them typically, we also have this rule that we call Ohm's Law, I equals delta V over R. And so with some clever substitutions, we can generate two different forms for the power equation. These ones aren't given to you on your equation sheet, so it's worth remembering that you can combine these two equations. If I substitute in this delta V over R here in the I spot, I'm going to get P equals delta V over R times delta V, or just delta V squared, over R. My other option here would be to rearrange the Ohm's Law equation to get delta V all by itself. So that one would read delta V equals I times R. And so if I plug that in, I'd have P equals I times and I times R, which gets us just I squared times R. So two ways to calculate the power dissipated through a resistor. Actually, three ways, I guess, with the white, the red, and the blue equations given here. Keep in mind here, as I said, this is the only equation that's given to you on your equation sheet. So we need to be aware that, yeah, we can combine those two, or we can use Ohm's Law to figure out something that we don't know for this power equation. There are some additional units we should be aware of that get used sometimes with electricity. Kilowatt hours is one that, if you've ever looked at an electric bill, you've seen kilowatt hours. So your electricity is billed and how many kilowatt hours of electricity you use. Now, kilowatt, we know, is a unit for power, and hours is a unit for time. And the equation we were dealing with before was power equals delta E over T, delta T. If we rearrange this equation, so as power times time, that'd be equal to energy. So kilowatt hours is actually an energy unit. Now, how much energy is that? Well, if we take the power as 1 kilowatt, that's 1,000 watts or 1,000 joules per second, times 1 hour, which is the same as 3,600 seconds, we get an energy here of 3,600,000 joules. So a kilowatt hour, that's a pretty big measure for energy. Now our other unit that we should be aware of here is amp hours. Batteries are always rated in amp hours. So if we look at the units on this one, amp, that's a measurement of current. And hours is a measurement of time. And we don't have an equation outright that relates current and time, except for, well, the definition for current. Current is the rate at which charge flows through a certain point. And so we could think of the units on this. An amp, remember, that's the same as a coulomb per second times, so this is 1 coulomb per second, times 1 hour, it's 3,600 seconds. So this is just the same as 3,600 coulombs. If something has 1 amp hour for its rating, what we're talking about there is the amount of charge that it can generate. So batteries, we generate charged particles by doing chemical reactions. So we have enough of our chemical reactants in there to generate 3,600 coulombs worth of charged products for every amp hour of rating that it has on there. Now, kilowatt hours, we could think of this as meaning how much energy we use. If something uses energy at a rate of 1 kilowatt and we run it for 1 hour. For amp hours, it'd be how much charge we'd have to have. We have 1 amp of current running for 1 hour. So they both have those hours units in them, and so we'll be able to relate those ideas with each other later on. Let's take a look at an example of that now. So, the question we've all asked at some point, I think, when buying batteries is, does the brand matter? Or what, specs on the battery matter? Does it matter whether it's Ultra, Maximum Plus, or just the regular store brand? Well, you can take your own opinions on that, but I can tell you that definitely the rating, the amp hour rating on those batteries makes a difference for how long those batteries are going to last. That's basically going to give us that information, 15 amp hours. So if we were running a 1 amp circuit with this battery, it can last for 15 hours. So let's look at this circuit and figure out how long it's going to last in this circuit. Now, 15 amp hours, like I said, means if we ran a 15 amp circuit, if we had a current of 15 amps coming from this battery, it could last for 1 hour. But do we have 1 amp of current? Well, let's go ahead and do Ohm's Law to figure out how much current we have here. So I will say current equals voltage divided by resistance. And here we're looking for the voltage across this 500 ohm resistor and the current through that resistor and the resistance of that resistor. So the current is going to be the delta V across this resistor We know it's 5 volts from this side of the battery to this side. We have nothing but wire connecting there, so 5 volts from here to here as well. Wires all the way along here. So 5 volts across that battery divided by 500 ohms gives us a current of 0.010 amps. Okay, now you could probably do a little mental math here. If it were 1 amp, it would last for 15 hours. If it were 1/10 of an amp, it would last for, well, it'd be more time then if it's a less current. So it'd be 150 hours there. And if it's 100th of an amp, like this one is, that'd be 1,500 hours. Or you could think of this in terms of charge. So current is equal to charge divided by time. And we want to figure out what the charge is, so we'll use Q. And we want to know how long this thing is going to last, so we need to know about the time. So I'll rearrange this. Time will be equal to Q divided by I. Our charge here is 15 amp hours. So 15 amp hours. And let's go ahead and do a conversion here to get this into coulombs. We said in the last slide, let's see, it's 1 coulomb per second for 1 amp, and 3,600 seconds per an hour. So it's 3,600 coulombs for 1 amp hour here. So that's per amp hour. And then we'll divide this by the current, which is 0.010, and that's coulombs per second. This is a great time to double check and make sure our units work out, that we haven't done something funky here. So we've got hours on top here, cancels with hours on bottom here. Amps on top here, cancels with amps on bottom. Let's see, coulombs on top and coulombs on bottom cancels. So we're left with 1 divided by 1 divided by seconds. So no units divided by no units divided by seconds. So that's just seconds left for our answer. And so when we calculate this, we find a time of 5,400,000 seconds to exhaust this much charge, or about 1,500 hours, or exactly 1,500 hours here, which we, again, figured out just kind of reasoning our way through the units earlier on. Now, let's look back up top here and think about how much internal energy we're going to have developed in this resistor by the time the battery dies. Well, energy, the only relationship we have for that is the one with power. So I first need to figure out the power dissipated through this resistor when we have this setup, and then I can multiply the power by the amount of time to get the energy. So I'm using the equation power equals energy divided by time. Multiply both sides by time to get energy all by itself. So I'll begin by calculating the power. Power is equal to the current times the voltage across this resistor, which in this case is equal to 0.010 amps times 5.0 volts. And so we're going to get 0.050 watts, or joules per second. And I think the units joules per second are good ones to use here, because it reminds us the relationship between energy and power. If I want energy, that's going to be the power, the rate at which we're generating energy, or changing energy rather, times the amount of time. So we've got our power of 0.050 watts times time of 5,400,000 seconds. Gets us our total energy change, which is 270,000 joules of energy. It has been changed from chemical energy in this battery to eventually internal energy in this resistor, and then that dissipates into the environment. But that's the amount of energy anyway. So that's kind of putting these different ideas together. Amp hours, kilowatt hours, some special units definitely to be aware of with this stuff. Kilowatt hours, especially with pricing, they might say something like an electric company charges 15 cents per kilowatt hour, and you use a light bulb this way for so long, so how much is it going to cost you? So just keep in mind that kilowatt hours is kind of a funky unit for energy. I would go ahead and just change it to joules, and then you'd be good to go on this. So one last thing that we can do with this, 270,000 joules, how many kilowatt hours would that be? And you don't have the conversion for kilowatt hours given to you anywhere, so I would just calculate this every time. So 1 kilowatt hour is 1,000 watts, 1,000 joules per second, times an hour is 3,600 seconds. And so this is 3,600, and then add 3 more zeros, and that's joules per second times seconds, so that's just joules. So 3,600,000 joules. I'm dealing with 270,000 joules. So this answer can be expressed then, if I divide 270,000 by 3,600,000, as 0.075 kilowatt hours. Not much on that scale, but an equally valid way to express the amount of energy dissipated through this resistor.